morning, everyone. Today is Friday, May 29th. It's early morning. And today, I want to talk to you about the foundation. The foundation beneath everything. What a foundation actually is, why it exists, and how buildings have built them for 12,000 years. This is part 1 of 10. What a foundation actually is, why it exists, and how buildings have built them for 12,000 years. Imagine you are standing in a field on a summer afternoon, holding a beach umbrella. You push the spike into the ground and it holds perfectly fine, right up until the moment a gust of wind hits the fabric, turns it into a sail, and yanks the whole thing out of the earth. You already understood at an intuitive level everything a structural engineer spends years formalizing. The ground is not infinitely strong. Loads travel downwards and sideways and sometimes upward. And the connection between a structure and the earth beneath it is the single most consequential engineering decision you will make. That connection is the foundation. In this series, 10 long, exhaustive articles published daily, we are going to cover every type of foundation used in every type of building, from the simplest garden shed to 40-story apartment towers. We will talk about soil science, frost depth, expansive clay, seismic zones, waterproofing, drainage, code requirements, inspection questions, repair methods, and specific case studies in Newport News, Virginia, Dallas-Fort Worth, Texas, and Kathmandu, Nepal. We will explain everything from first principles. We will assume you are not a civil engineer. We will cite every claim that needs citing, and we will not stop until there is nothing left to say. The first article is about foundations as a concept, what they are, what forces they resist, why some work and others fail, a brief history of how humans figured it all out over millennia, and the vocabulary you need to understand every article that follows. Buckle up, the ground beneath your feet is far more complicated than it looks. Part 1. What is a foundation really? A foundation is the structural element or system of elements that transforms all loads from a building into the earth below it. That sentence is short, but each word carries weight. So once again, a foundation is the structural element or system of elements that transforms all loads from a building into the earth below it. So, structural element. A foundation is not just the bottom of the house. It is an engineered component with specific geometry, specific materials, and specific connections to both the structure above and the soil below. A random pile of stones is not a foundation. A concrete pad poured to engineering specifications is. Transfer loads. The foundation's job is not to hold things up in the way that a column holds up a beam. Its job is to spread loads out. The building above concentrates enormous forces. the weight of every wall, every floor joist, every roof truss, every piece of furniture, every person, every snow accumulation into relatively small points. The foundation catches all of these concentrated forces and redistributes them across a large enough area of soil so that the soil can accept them without moving. All loads, not just gravity. We will spend a great deal of time on this. The foundation resists dead loads, live loads, snow loads, wind loads, seismic loads, hydrostatic pressure, expansive soil pressure, frost heave, uplift. So dead loads, the permanent weight of the structure itself, concrete, steel, wood, glass, insulation, roofing, mechanical systems. These do not change. Live loads, occupancy loads, people, furniture, stored goods. These change constantly but are bound by code. Snow loads. In cold climates, accumulated snow can weigh 20 to 40 pounds per square foot or more. This matters enormously for roof design, which then flows into foundation design. Wind loads. Wind pushes horizontally against walls, creating an overturning force at the base. The foundation must resist these or the building tips. Seismic loads. Earthquakes accelerate the ground horizontally. The foundation must transfer these accelerations to the structure without the two separating, and the structure must return to plumb without the foundation having walked sideways. This is an entire subdiscipline of engineering. Hydrostatic pressure. Water in the soil presses against basement walls. If the foundation is not designed for it, water wins. Expansive soil pressure. Certain clay soils swell up when wet and shrink when dry. The pressure they can exert, easily 10,000 pounds per square foot, is sufficient to crack any concrete if not properly handled. Frost heave. Water in soil expands by about 9% when it freezes. If that expansion occurs under or alongside the foundation, the forces can lift or tilt an entire house. Uplift. In high winds and some seismic events, part of the structure experiences upward forces. The foundation must anchor the building down, not just support it up. Into the earth below it. The earth is not a uniform material. It is a geological layer cake of varying materials. Topsoil, clay, silt, sand, gravel, rock, each with different strengths, compressibility, drainage, and frost sensitivity. A foundation that works brilliantly in sandy coastal Virginia will crack in half in Dallas clay. A foundation appropriate for a cabin in Vermont will fail in earthquake country unless it is bolted into the concrete in a specific way. The earth is the other half of the structural equation, and ignoring it is the single greatest cause of foundation failure. The three fundamental requirements of every foundation, regardless of type, size, climate, or budget, every successful foundation must satisfy three basic requirements. These are not engineering preferences, these are physics.